These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. So you're taking organic chemistry, right?
Yes.
Okay. For the next exam, it looks to me like the most important reactions will be SN1, SN2, E1, and E2. Are those all reactions you guys have covered?
Mm-hmm.
Okay, so shall we start by talking about those types of reactions?
Actually, the stuff we were gonna talk about first, I think he's focusing on the alkyl halides and alcohols and ethers.
Right, but those are functional groups that go through SN1, SN2, E1, and E2 reactions.
Okay. Could you explain those reactions? He only
Yeah.
just started talking about them today
Sure.
in lecture.
Okay. Yes. All right. So let's start with, say, a SN2 reaction. Or maybe we should start by, yeah, okay. So let's say, look at this. Okay, so let's see if we can predict what would be a reasonable reaction here. So we need to go over some basic terminology you'll use a lot in the course. Have you heard the term nucleophile?
Yes.
What is a nucleophile?
I think it literally means nucleus loving, so they are attracted to positive charges. Typically, they have negative charges.
Good, that's a good answer. What do nucleophiles do in reactions?
They'll take extra negative charge, like they'll take a lone pair.
Okay, so you're saying that they will receive electrons.
Mm-hmm.
Now, if you think about it, that contradicts what you said before, because you said that nucleophiles tend to be negative, right?
Sorry, I'm a little bit tired.
No, that's fine. Yeah, but do you see how that's... so what would the nucleophile do? Donate or receive electrons?
It would give away its electrons.
Yeah, so a nucleophile donates electrons to join something.
Yeah.
So is the nucleophile going to tend to be something that started negative or started positive?
It'll start negative.
That's what makes it want to donate electrons. And I think you were remembering, why is this called a nucleophile? Because what's the charge on a nucleus?
Positive.
So this is really just a fancy way of saying a positive lover, because the nucleus is positive, it has the proton. This is a positive lover. That makes sense because it tends to start negative, unlike charges attract. So something that's negative tends to want to be close to something that's positive. Now, in nature, do you think nature likes charges or dislikes charges?
Dislikes.
That's right. So does nature want things to be neutral or charged?
Neutral.
That's right. That's why if you tend to start negative, you want to donate your electrons to get back to being neutral. If you tend to start negative, you want to donate your electrons to be neutral. So taking a look at these substances here, who would be a good nucleophile?
The bromine, or the bromide.
The bromide. So does that mean that the bromide should go at the head or the tail of an electron pushing arrow?
The tail.
That's right. Those are terms we'll be using quite a bit, so just to make clear, is this the head or the tail?
That's the tail.
So what would we call this?
The head.
That's right. Now, what does the electron pushing arrow mean? It means that the thing at the tail is donating electrons to the thing at the head. These show the movement of electrons. So in this example, we would want to draw an arrow like this. The bromide should go at the tail. So in general, nucleophiles tend to go at the tail of electron pushing arrows. We could draw that like that. That's an important idea. So nucleophiles tend to have negative charges. Did you get I just sent you an email a couple minutes ago. Did you get the email I sent you with the handouts?
No, I actually just got home.
Okay, that's fine.
I can pull it up on my phone.
You might want to pull that up.
Okay, yeah, I see it.
I sent you 2 handouts. Let's look at this
one.
Yeah,
2 files on here.
On reactivity.
Okay.
So here on the first page of that reactivity handout, so here's a summary of nucleophiles. The nucleophile donates electrons to join something. So the nucleophile goes at the tail of an electron pushing arrow. The best thing to make something a nucleophile is a negative formal charge, which is what we had on this problem, the negative formal charge on the bromide. What would you do if there was nobody with a negative charge? Well, then you would look for a partial negative charge or a lone pair. Those are the ones that we'd probably be working at now. It turns out that nucleophiles are very similar to bases, so a lot of the things for bases are also true, so we'll probably keep referring to that. Okay, so the next thing we have to do in this reaction is figure out who's going to be the electrophile. What is an electrophile?
It's basically the opposite of a nucleophile. It's wanting to receive electrons.
In the reaction, it will receive electrons to join something.
Mm-hmm.
You can tell that from the name because phile means lover, so this is an electron lover. Since it's an electron lover, it wants to receive electrons to join something. So will this tend to start with a positive or a negative charge?
It would start with a positive charge.
Either a full positive, which is best, or a delta positive. And would an electrophile tend to go at the head or the tail of an electron pushing arrow?
At the head.
Like so, because it wants to receive electrons. Okay, so let's take a look at this reaction that we were just looking at. Which atom here would be a good electrophile?
The iodine.
So you would predict a reaction like this?
Mm-hmm.
Okay, now let's talk about that a little bit more. The first thing you should be looking for here is somebody with a positive formal charge. And it turns out nobody here has a positive formal charge. If they did, it would already be drawn. So the next thing we have to look for is a delta positive. Have you seen that symbol before of delta positive?
Mm-hmm.
Okay. So we need, now formal charges are generally going to be drawn for you, but delta positive and delta negative you have to figure out. So let's look at this molecule again. Who in this molecule has a delta positive charge and who has a delta negative charge?
Oh, well, I guess iodine is more electronegative than the carbon, right?
Yes, that's good.
So it'll have a partially negative charge.
And who will have a delta positive charge?
The carbon.
Yeah, which carbon? 1 or 2?
Both of them, or just 2?
Now, remember, why does the iodide have a delta negative? Who did it take these electrons from?
Oh, the only one it's bonding with, so 2.
Yeah, 2. It's not attached to carbon 1, so it can't take many electrons from carbon 1.
Okay.
And so what's going to be the charge? So who's going to have the delta positive?
Carbon 2.
Carbon 2 will be delta positive. That's right. Now, what about the bond between 1 and 2? Well, let's go back to this. How did you know that the iodide wanted electrons more? How did you know it was more electronegative? Because it's further to the right in the periodic table, and carbon was further to the left. How about if you compare carbon 1 and carbon 2? Well, those are both carbons, so they're not going to be pulling electrons away from each other. So there's no delta positive or delta negative just because of those bonds. Also, we have a bunch of hydrogens.
Yeah.
Everybody has a bunch of hydrogens here. Not everyone, for some reason this isn't drawing. Not everyone is aware of this, but a hydrogen is similar to carbon in electronegativity. You can't use the periodic table to find the electronegativity of hydrogen. Hydrogen is similar to carbon, but that again tells us that the hydrogen-carbon bonds are not going to create delta positives or delta negatives, so we don't need to worry about those. Okay, so now that we've assigned those delta positive charges, which atom in the molecule would we expect to be the electrophile?
The second carbon.
Number 2. And I think that was different from your first guess. At first you were guessing the iodide. All right, so this is an important rule that we'll be using over and over in this course. The electrophile is the thing with the positive charge. It would be best if it had a full positive charge, but if you can't find a full positive charge, then you have to assign the delta positives yourself. I can see why you thought it might be the iodine, because iodides are electronegative, so you would think that they want electrons, but notice the iodide has already picked up electrons from the covalent bond. Now that the iodide's already picked up a delta negative from the covalent bond, it's not really that eager to get more electrons. Okay,
Yeah.
so now we've assigned those. So let's take another look at that handout. These are rules that you'll want to internalize and use over and over in the course. So an electrophile is something that receives electrons to join something. It turns out that that's pretty similar to an acid. The electrophile goes at the head of the electron pushing arrow. First, you would look for a positive formal charge, which would generally be drawn for you. But if there are no positive formal charges, then you yourself have to look for the delta positive charge. First, for an electrophile, you would look for a positive formal charge, which would be drawn for you. But if you don't see a positive formal charge, then it's your job to assign the delta positives and the delta negatives, because those are not drawn for you. And that's what we did here. So we should also go to page 2. How do you assign the delta positive charges? Well, first of all, you only have to do that if there's no formal charge. If there's no formal charge, then you might already know these rules. If you have two identical atoms, they don't give each other a delta charge, like the carbons that were bonded to each other. Also, a carbon that's bonded to a hydrogen does not give a delta charge, because hydrogen is similar to carbon. And other than that, you just compare where they are in the periodic table. The atom to the left gets the delta positive, and the atom to the right gets the delta negative. Iodide is to the right of the carbon, so it gets the delta negative, and the carbon gets the delta positive. For organic chemistry, it doesn't really matter very much what row you're in. For organic chemistry, only the column is really important for assigning the delta positives and the delta negatives. Okay, so that's our rule. Now, this arrow by itself can't be the end of the story. Can you see why this can't be the only arrow? Because carbon-2 already has a complete octet. So it wouldn't be legal for it to receive these electrons unless it was also losing some electrons. So we're also going to have to put in another arrow like this to show the electrons that are leaving to make room for these new electrons. So we also need to say what role the iodine is playing. Remember, the bromine is playing the role of the nucleophile. Carbon-2 is playing the role of the electrophile. Do you know what a good name would be for the role that the iodine is playing?
The leaving group.
That's right. How would you define leaving group?
It's getting a pair of electrons, or it's getting the electrons from the bond and going away from the rest of the molecule.
That's actually a very, very good definition. Yes. So it receives electrons to leave something. The key part that most people don't realize is that leaving groups always receive electrons. And that way they're similar to electrophiles. But where an electrophile is receiving electrons to join something, the leaving group is receiving electrons to leave something. So would a leaving group tend to start with a positive or a negative charge?
A positive charge?
It tends to start with a positive formal charge, not with a delta positive charge. Now, notice that in this molecule, there were no positive formal charges. And I just said that you don't use delta positives for leaving groups. So how would we find the leaving group otherwise? Well, you just need to memorize that chlorine, bromine, and iodine, neutral chlorine, neutral bromine, Chlorine, bromine, and iodine with neutral formal charges are all good leaving groups.
Okay.
And here we have an iodine, an iodine with no formal charge, so that's a good leaving group. Again, that shouldn't surprise us that it's willing to receive electrons because it is highly electronegative. All right, so this would be a reasonable leaving group because it's a chlorine, bromine, or iodine, and it is receiving those electrons. So going back to the handout, a leaving group is something that receives electrons to leave something. So it goes at the head of the electron pushing arrow. I forgot to write that down, but you can see that from our picture.
Mm-hmm.
First, you would look for a positive formal charge, but if there's no positive formal charge, then you look for a halogen with zero formal charge, like chlorine, bromine, or iodine. So that just has to be memorized. Okay, so now we're ready to draw the product of that step. And we're supposed to use the arrows to draw the product. So here's a good method for drawing the products. This is on page 2 of that handout. Oops. First, you want to redraw the starting materials. Then you look at each electron pushing arrow, and if the arrow is breaking a bond, you erase that bond, and if it's forming a bond, you draw the bond. So let's look at this arrow. Do you think this arrow tells us to erase a bond, to form a bond, or both?
Both.
Now,
Wait. Just to make a bond.
Just to make a bond. How would you tell if it was telling you to break a bond? That's the next little table. You're only going to break a bond when the tail is on a bond. You break a bond when the tail is on a bond, but this tail is on the negative formal charge, so we're not breaking a bond. So this arrow is only forming a bond. We're going to form a bond between which two atoms, according to this arrow?
Bromine and carbon.
Good. Which carbon?
The second one.
That's right. So we always have to be as precise as possible. So I'm going to draw a new bond between the bromine and the iodine. Then we go to the next electron pushing arrow. Does this arrow tell us to break a bond or to form a bond or both?
Break a bond.
It only tells us to break a bond. Here the tail is on a bond, so we're breaking the bond. We're going to break the bond between which two atoms?
Iodine and carbon.
Which carbon?
The second one.
That's right. We always have to be precise as we can. This is like math. Okay, so now we've done that. Now that's all the electron pushing arrows. So then we have step 3. You make the atom that's losing electrons from the initial tail one step less negative. Do you see what I mean by initial tail? This would be the initial tail because it's at the beginning of the string of arrows. This is not the initial tail because it's in the middle. And this is what I would call the final head because it's at the end. This is not the final head because it's in the middle. So in this problem, which atom was at the initial tail?
The bromine.
So what should be its new charge?
It should be neutral.
Because it started negative, and we're going to make it one step less negative. And how about the which is the atom that's at the final head?
The iodine.
That's right. And what should its new charge be?
Negative.
Because it's going to become one step more negative. That should be obvious from the arrows, because it's receiving electrons. It started with a neutral formal charge, and it received electrons. Notice that what we're doing here is we're assigning, I should have put in the handout that we're assigning the formal charges. So the delta charge makes no difference to this. We're not adding a negative to a delta negative, we're adding the negative to the zero formal charge. This is a process that has nothing to do with the delta charges. And now I think we're done. Now we have the product. A lot of people don't realize that the arrows are supposed to make it easy and obvious to draw the products, but most people don't know these rules. So it's really important to internalize these rules. If you use these rules on every problem, the arrows should make it easy and obvious to draw the products. We're not supposed to have to guess. How do you know what arrows to draw? Well, that's what the first page is about. The first page has the rules for knowing who goes at the heads and the tails of the arrows in the handouts. So this is the reaction, and this is what's called a SN2 reaction. Obviously, now that we've internalized the rules, we have to learn how to get through these reactions faster and faster so that we don't have to think about each step. But to start with, you have to think about why each step makes sense. Do you know what the S stands for in SN2?
No.
So it stands for substitution.
Okay.
There's three main types of reactions in organic chemistry. Three main types of reactions: addition, elimination, and substitution. So this is a substitution reaction. Why do you think it's called substitution? Who are we substituting for who?
You're substituting the bromine for the iodine?
That's right. So a substitution reaction is when you substitute one group for another. Now, what does the N stand for in SN2? It stands for nucleophilic substitution. This thing that's getting attacked here, we could call the substrate. So this is called nucleophilic substitution because there's a nucleophile that's attacking the substrate. It's called nucleophilic substitution because it's the nucleophile that causes the substitution to happen, so to speak. The nucleophile substitutes for the leaving group. So it's a nucleophilic substitution. Okay, good. And why is it called SN2? That's actually a little bit complicated, so maybe we'll come back to that in a few minutes. We're maybe not quite ready for that yet. Now, obviously we drew two arrows here for the SN2, but what we've just drawn here is what's called the mechanism of the reaction, how it happens. How many steps are there in an SN2 reaction? How many steps did we just draw in this SN2 reaction?
2.
Now, you might have said that because there's two arrows, but the key thing is both of these arrows happened simultaneously. We drew them both at the same time. So there's two arrows, but there's only one step.
Okay.
That turns out to be very important. SN2 is a one-step reaction because the two arrows happen simultaneously.
Okay.
If they weren't, you can see we drew them simultaneously, and that turns out to be quite important. We'll see why as we go on. Okay, so this is our SN2 type reaction. So what happens in an SN2 reaction? Maybe I'll look at the other handout now. Page 3, of the other handout. What happens in an SN2 reaction? Well, it's one step where the nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. So that's a more important terminology I should have mentioned. The carbon that's attached to the leaving group is called the alpha carbon. So in this case, carbon 2 was the alpha carbon. The carbon attached to the leaving group is called the alpha carbon. So in this one step, the nucleophile joins the alpha carbon and the leaving group leaves the alpha carbon. You were mentioning that your instructor went over these reactions pretty quickly. So this is what SN2 is. This is what SN2 means. It's a nucleophile joining the alpha carbon and the leaving group leaving the alpha carbon. We could also call the alpha carbon the electrophilic carbon. So the nucleophile joins the electrophile and the leaving group leaves the electrophile. So for every SN2 reaction, you have to decide who's going to be the nucleophile, who's going to be the electrophilic carbon, and who's going to be the leaving group. And you can do that using the rules that we were just talking about. And then we need to practice so we can get through those quicker. So I'm going to tell you this is going to be another SN2 reaction. And now your job is to draw the electron pushing arrows. You should do this on paper, but since I can't see what you're writing, you'll need to tell me what you're writing down. So what I need you to tell me is exactly where you're putting the head and the tail of each electron pushing arrow.
Okay. So first, you've got chlorine is a nucleophile. It's a chloride ion because of the negative charge.
Good.
So you have the tail on that end.
Good.
And then it goes towards the first carbon. Because bromine is more electronegative than carbon. So bromine will have a partial negative charge, and carbon will have a partial positive charge.
Carbon 1. Good.
Carbon 1, yeah. And then you have an arrow starting at the bond between carbon 1 and bromine. And it goes towards the bromine, like the head is at the bromine.
Excellent.
And that's the leaving group.
That's right. How do we know that the bromine is an acceptable leaving group? Because we've just memorized that bromine is an acceptable leaving group. Okay, that was good. One thing you did there was very good is you didn't just draw the arrows, but you explained to yourself why each one was reasonable. That's something you always have to do, make sure that each arrow is reasonable, and you did a good job of doing that. So now we need to draw the products from that step. So remember, you should start by just redrawing the starting materials. And now you need to tell me exactly which bonds you're going to erase, exactly which bonds you're going to form, and which charges you're going to change.
Okay. So you form a bond between carbon 1 and chlorine.
That's what this arrow tells us to do. Good.
Mm-hmm. And then you erase the bond between carbon 1 and bromine.
That's what this arrow tells us to do. Good.
Mm-hmm. And then you change the charge of chlorine to 0.
Because it's at the initial tail. Good.
Mm-hmm. And then you change the charge of bromine to a negative.
Because it was at the final head.
Yeah.
Okay, excellent. All right, so that went much faster than the first one. So the point is, once you learn the rules, you need to learn how to get through these more quickly. So that was good. Okay, so then this was an SN2 reaction. What does the S stand for?
Substitution.
Who are we substituting for who?
Sorry?
Who are we substituting for who in this reaction?
We're substituting chlorine for bromine.
That's right. And what does the N stand for?
Nucleophilic.
Nucleophilic. It's called nucleophilic substitution because it was prompted by the nucleophile attacking. How many steps were there in this SN2 reaction? How many steps are there in this SN2 reaction?
1 step.
That's right. So notice that the number 2 here is misleading. This does not stand for 2 steps. We haven't said yet what it stands for. So there's only 1 step in this reaction. Okay, good. Very good. So now we need to kind of learn what the properties of a SN2 reaction are. Have you heard of the concept of a rate determining step?
Mm-hmm.
Yeah. So remember, is the rate determining step the fast step or the slow step?
The slow one.
The slow one. And that's, so if you want to speed up a reaction, you need to speed up the rate determining step. That's the step that matters. Here's kind of a trick question. What's the rate determining step in an SN2 reaction?
Well, there's only 1 step.
Yeah, there is only 1 step, so that's the rate determining step.
Yeah.
Now, that might seem obvious, but what that means is, remember, only the things that participate in the rate determining step matter for the speed of the reaction. Only the things that participate in the rate determining step matter for the speed of the reaction. But notice that for SN2, everybody participates in the rate determining step because there is only 1 step. So for example, does the nucleophile strength affect an SN2 reaction? Yes, because it's in the rate determining step. Does the leaving group ability affect the rate of an SN2 reaction?
Yes.
Yes, because it's in the rate determining step. Does the electrophile ability of the electrophile affect the rate of an SN2 reaction?
Yes.
Yes. Those might seem obvious, but that's only because they're all in the rate determining step. Pretty soon we'll see other reactions where some of those things are not in the rate determining step, so they don't affect the rate. So notice that the nucleophile here joins in the rate determining step. So what matters is how easy it is for the nucleophile to join the substrate. The key thing here is to memorize what's the big obstacle to SN2. Well, let's say that there was a lot of steric hindrance around carbon 1. Have you ever heard of that term, steric hindrance?
Yeah, I've heard of it.
Okay. So steric hindrance just means things that get in the way of other things. Steric hindrance means things that get in the way of other things. So if there was a lot of steric hindrance, do you think that would speed up or slow down the SN2 reaction?
Would slow it down.
That's right, because things would be getting in the way of the nucleophile. So we need to memorize that's the big obstacle to SN2 reactions. The big obstacle to an SN2 reaction is steric hindrance that blocks the nucleophile. So the more steric hindrance there is, the harder it will be to have a SN2 reaction. So as we go, we'll see how that becomes very important. So for example, which of these two cases do you think would have a faster SN2 reaction?
Probably the first one.
That's right. Why would this one be slow? What would slow down the SN2 reaction here?
Because the alpha carbon is connected to more carbons.
That's right. So there would be steric hindrance that would block the reaction in this case. Let's be specific here. Which is the alpha carbon in this molecule?
6.
And which is the alpha carbon in this molecule?
2.
That's right, because the alpha carbon is the one that's connected to the leaving group. Have you heard the terms primary, secondary, and tertiary?
Yes.
So is the alpha carbon here primary, secondary, or tertiary?
Be primary.
Because it's connected to one carbon chain. And is the alpha carbon here primary, secondary, or tertiary?
Tertiary.
Because it's connected to three carbon chains. So in general, who's best for SN2? Primary, secondary, or tertiary?
Primary.
That's right. So we could make a list. The rate of the SN2 would be greatest for primary and smallest for tertiary. Actually, there's someone else that's even faster. What would we call this alpha carbon? Well, this alpha carbon isn't even primary because it's not attached to any carbon chains. You would call it a methyl alpha carbon. So would methyl be the fastest or the slowest SN2?
The fastest.
Because it has the least steric hindrance. So this is a table of rates. The rates is greatest for methyl and slowest for tertiary. One thing that you're likely to see on the test is they like to give you a problem and say, rank the following substrates in order of the rate of the SN2 reaction, which would go fastest and which would go slowest. So this is one important tool for answering that type of question. By the way, you mentioned that what your instructor was focusing on now were things like alcohols and alkyl halides. Well, you can see how this is relevant because this is one of the major reactions that an alkyl halide goes through. What we've been looking at is alkyl halides. They go through SN2 reactions, and maybe we'll see later that alcohols also go through those SN2 reactions, as well as other reactions we'll try to get to. Okay, so here's these ideas. Now, in fact, it turns out that tertiary alpha carbons have so much steric hindrance that they can't really do SN2 at all. SN2 is basically impossible for a tertiary. So you can really only do SN2 for a primary or a secondary or a methyl. So that's something that has to be memorized. If you have a tertiary, there won't be an SN2. So can this do an SN2? Yes. Can this molecule do an SN2 reaction?
No.
No. So there will either be no reaction or some different reaction that we'll have to get to later. But this definitely can't do an SN2 because it would be too slow because there's too much steric hindrance. Okay, good. Now, something else that you might have to do, so we basically learned here how to rank which are the best, which are the best alpha carbons. For SN2, the best alpha carbon is one that has low steric hindrance. That might be different for some other reaction. Now, we also have to think about the nucleophiles. Does the nucleophile participate in the rate determining step for SN2?
Yes.
Because there is only one step, so it's participating. That means that the nucleophile quality matters for SN2. We need a good nucleophile. What would be a good nucleophile? Well, we know that one thing that makes something a good nucleophile is a negative charge. So, for example, these would tend to be good nucleophiles. Here's something else that has a negative charge that's a good nucleophile. On the other hand, though, there are some things that are neutral that are still good nucleophiles. For example, if you have a lone pair, a neutral nitrogen with a lone pair is still a good nucleophile. Or say a neutral sulfur with a lone pair is still a good nucleophile. It turns out there's only one thing that would qualify and so I guess something else that would be a good nucleophile is an oxygen with a negative charge. I guess I should put that over here. Oxygen with a negative charge is also a good nucleophile. There's only one thing that qualifies as a poor nucleophile, which is a neutral oxygen. Oxygens with no formal charge, they can still be nucleophiles because of their lone pair, but they're a poor nucleophile. This is really the only thing in this category. There's lots of good nucleophiles, but this is the only thing that would really qualify as a poor nucleophile. Okay, so the key is, remember, SN2 needs a good nucleophile because the nucleophile participates in the rate determining step. SN2 needs a good nucleophile. What that means is this can't do SN2. A neutral oxygen with just a lone pair can't do SN2 because it's not a good enough nucleophile. All of these can do SN2. There's lots of things that can do SN2. There's only one type of atom that can't do SN2. Okay. Notice that there are some neutral nucleophiles that can still do SN2. Here's some neutral nucleophiles that can still do SN2, but the oxygen can't. You can kind of see why. Is oxygen highly electronegative or not very electronegative?
It's really electronegative.
The only thing that's more electronegative than oxygen is fluorine, because oxygen is far to the right. Does that mean that the oxygen really wants to donate electrons or hold on to its electrons?
It really wants to hold on to them.
That's right. So would that make it a good nucleophile or a poor nucleophile?
A poor one.
So we just explained why oxygen is the only thing in this category. It has a lone pair, so it's a nucleophile, but it's so electronegative that it's not really that eager to donate those electrons. So that's the explanation for why a neutral oxygen goes here. On the other hand, neutral nitrogen or neutral sulfur, those are not as electronegative. So they actually are good enough nucleophiles to go in the good nucleophile column. Okay, so that's an explanation, but you should probably just memorize that neutral oxygen is the one thing that can't do a SN2 type reaction. So for example, let's say we've got So let's compare these two reactions. If we were going to do a SN2 reaction here, who would be the nucleophilic atom?
The NC minus.
That's right. This is what's called a cyanide anion. Now, the negative charge in cyanide is on the carbon, not on the nitrogen. That's something that maybe you should memorize. So who's the
Okay.
nucleophilic atom, the nitrogen or the carbon?
The carbon.
Carbon 7. Good. If we were going to do a substitution reaction here, who could possibly be the nucleophilic atom?
The oxygen.
Because it has a lone pair.
Mm-hmm.
Now, going back to here, can we do an SN2 reaction with these reagents?
Yes.
Can we do an SN2 reaction with these reagents?
No.
No. Why not? Because, as we were just saying, neutral oxygen is not good enough for SN2. It could do other substitution reactions, but it can't do SN2. So here, there will be no SN2 reaction. So there'll either be no reaction at all or some other reaction we'd have to learn about later. But it certainly can't do SN2 because it's a neutral oxygen. When I say neutral, I mean no formal charge. This has no formal charge, so it can't do. This is an oxygen with no formal charge. A delta negative charge is not good enough for the oxygen. Whereas here, we said that all the other nucleophiles can do SN2. Cyanide can do an SN2, so we could do an SN2 reaction in this case. So those are two important rules that we need to learn for SN2. Our first rule for SN2 was this one. It only works for primaries, secondaries, and methyls, not for tertiaries. And this is our next rule that we learned for SN2. Most nucleophiles can do SN2 except for neutral oxygens. They can't do SN2. One thing you have to do on the test is decide what reaction is going to happen. So those are some important rules for determining the reaction that is going to take place. Okay, good. So who do you think is going to be the nucleophilic atom in this reaction?
The bromine.
That's right. How do you know it would be a good nucleophile?
Sorry?
How do you know the bromine would be a good nucleophile?
Oh, because it would have a negative charge.
A negative formal charge. That's right. But wait a second, I didn't draw the negative formal charge. How did you know the bromine has a negative formal charge even though I didn't draw it?
Because it's with sodium and they form an ion.
Great. Excellent. That's right. So that's good that you realized that. I said earlier that usually the formal charges will be drawn for you, but this is the one case where you're expected to draw them yourself. Anytime you have a non-metal that's bonded to a metal from the first or the second columns, that's automatically going to be an ionic bond. Anytime you have something that's bonded to something from the first one or two columns, that's going to be an ionic bond. So in this case, you're expected to draw the charges yourself. So we'd have to draw these charges ourselves. So it's good that you saw that. All right, so then where would you put the heads and the tails of your electron pushing arrows?
So you would put the tail at the formal charge on the bromine, and it would go towards the carbon 1. And then you would have another arrow going from the bond between carbon 1 and iodine going to the iodine.
Good. So what role is carbon 1 playing in this reaction? Nucleophile, electrophile, or leaving group?
Electrophile.
And how do you know it's a reasonable electrophile?
Because it's accepting the electrons from bromine.
That's true, but how do you know that it wants to do that?
Because it has a partially positive charge since iodine is more electronegative.
That's why you didn't say that carbon 6 or carbon 5 was the electrophile, because they don't have the delta positive charges. And what role is the iodine playing?
The leaving group.
And we know that's reasonable because we've just memorized that iodide is a good leaving group. So now we would read. So what's the name of the mechanism that you're doing here?
Substitution.
That's right. But what's the specific name for this specific type of
Okay, so
substitution?
SN2.
SN2. So I would say the general name for this type of reaction is substitution, and the specific name is SN2. How do you know this can really do an SN2? For example, how do you know this alpha carbon can do SN2?
Because it's secondary
That's
and
right.
not tertiary.
That's a good answer. Yes, it's secondary because it's attached to 2 carbon chains on either side. That's good enough for SN2. Very good. And how do you know that we can do SN2 with a nucleophile? Because this is not a neutral oxygen. We know that nucleophiles can generally do SN2 except for neutral oxygens. Okay, that's good. So now we need to redraw and then modify our picture. So you need to tell me which bonds you're going to erase and which bonds you're going to form and which charges you're going to change.
So you form a bond between bromine and carbon 1. And you erase the bond between carbon 1 and iodine. And you get rid of the formal charge on bromine. And you add a negative charge to iodine.
Good. And notice nothing happens to the sodium. The sodium is what we could call a spectator ion. The sodium is just a spectator ion. I told you earlier that positive charges make things reactive, but this is an exception. That doesn't happen for metals. When a metal has a positive charge, it's just a spectator ion. When the metal has the positive charge, it's just a spectator ion. So the sodium isn't doing anything. It's just spectating. Okay, so this is another example of a SN2 type reaction. Very good. Could we do an SN2 reaction here?
No.
Why not?
Because oxygen is a poor nucleophile, like neutral oxygen is a poor nucleophile.
That's right. Can we do an SN2 reaction here?
Yes.
Yeah, so maybe we should do that. So where would you put the heads and the tails of your electron pushing arrows now?
So you'd have the oxygen has a negative charge.
You know that because it's got the sodium. Good.
And so that goes to the bond between iodine and carbon 2. And then the second arrow goes between that bond between carbon 2 and iodine to the iodine.
Good. This is a primary, so we know it can do SN2. And this is an oxygen with a negative charge. We saw that that can do an SN2 reaction. So then we need to redraw and modify. So which bonds do you need to form, and which bonds do you need to break, and which charges do you need to change?
So you need to form a bond between the oxygen and carbon 2. And then erase the bond between carbon 2 and iodine. And get rid of the charge on the oxygen. And make the iodine have a negative charge.
Okay, and this is just a spectator. Great. So this is something a lot of students don't realize. Notice the huge difference between this oxygen and this oxygen. How did you know this oxygen had no formal charge? Sometimes I see students put a negative charge here, but that would be wrong because hydrogen is not a metal. Remember, it's only when you're bonded to a metal that we can automatically assume ionic bonding and put in the charges. Remember that hydrogen is actually pretty similar to carbon in electronegativity. So this is going to be a covalent bond. So there's a huge difference between this oxygen with no formal charge and this oxygen that has a negative formal charge. By the way, do you know what's the name of the type of functional group we created here?
Oh man, I forgot all my functional groups.
Okay, that's all right. This is what's called an alcohol. I guess that's one of
Okay.
the functional groups that's going to be on the next test. I guess this is going to be one of the functional groups on the next test. You were mentioning they were going to be focusing on things like alkyl halides and alcohols. So notice that so far, almost all the examples I've been giving you were alkyl halides. Alkyl halides, alkyl halides. And now we're starting to expand. Now we're seeing that you can also use an SN2 reaction to make an alcohol if you use the
Okay.
right nucleophile. So as we go, we just have to learn more and more reactions and how they involve more and more functional groups step by step. Okay, so here we've made an alcohol. But notice we couldn't use this to make an alcohol because this water doesn't do an SN2 reaction in this case. Whoops. Oh, well, I shouldn't have said that. I should have just said you can't do an SN2 reaction here. Maybe there's another reaction we could do to make the alcohol, but not with the SN2. All right, so that would give us this example here. So again, notice that the huge importance of finding the formal charges. The formal charges allow you to explain what's going to happen in organic chemistry. They explain the difference between these two cases. Can we do an SN2 reaction here?
No.
Why not?
Because the alpha carbon is tertiary.
That's right. So in this case, even though we have a good nucleophile, this is tertiary with 3 carbon chains, so you can't do a SN2 reaction. Good. Okay. Has your class talked about stereochemistry yet?
Yes.
Yeah, they have. Okay. So the next thing we have to learn about is the stereochemistry for an SN2 reaction. That's almost always going to be tested. So one thing to realize is so far we've only been drawing, so far I haven't been showing geometry in any of the products. That is, I haven't used wedges and dashes. How do you know when you need to use wedges and dashes and when you don't? Well, in general, you need wedges and dashes for a stereocenter. Have you heard that term stereocenter before?
Yes.
Without a stereocenter, you don't need wedges and dashes. Does this molecule have any stereocenters?
I'm a little bit foggy on what stereocenters were.
Okay, that's
Sorry.
a good thing for us to review. A stereocenter is a carbon that's attached to 4 different groups. A stereocenter is a carbon that's attached to 4 different groups. For example, carbon 1 is not a stereocenter because 3 of the groups it's attached to are identical, 3 hydrogens.
Okay.
How about carbon 2? Is that a stereocenter?
No.
Why not?
It has 2 hydrogens.
It has 2 hydrogens. That's one reason it's not a stereocenter. How about carbon 3?
Same thing. It's not.
Right? How about carbon 4?
Same thing.
That's right. How about carbon 2 here? Is this a stereocenter?
Yes.
It is, What are the four things it's attached to?
It's attached to a bromine,
Mm-hmm.
hydrogen, a CH3,
Mm-hmm.
and a CH2CH3.
Okay, so it's good that you figured out here. Notice the stereocenter definition doesn't say that you have to be attached to four different atoms. It just says four different groups. Some people might think this is not a stereocenter because it's attached to two carbons, but the carbons are different because there's a methyl group on the left and an ethyl group on the right. So the point is, if there's any difference at all in the two groups that you're attached to, then they count as different. They don't have to be different atoms, they just have to be eventually attached to different atoms. So this would be a stereocenter. It's good to put a star for stereocenters. So I would put a star here to show this is a stereocenter. Are there any other stereocenters in this molecule?
No.
No. All right, so yeah, this was a stereocenter with four different groups. Is carbon 1 a stereocenter here?
Sorry?
Is carbon 1 a stereocenter in this molecule?
Yes. No. Wait. No.
No, because if you think about the clockwise path, if you travel the clockwise path, you would meet exactly the same types of atoms as if you travel the counterclockwise path. There's no difference between the clockwise and the counterclockwise paths, so there's no stereocenter here. Is carbon 1 a stereocenter in this molecule?
Yes.
Yes, because now the clockwise path is different from the counterclockwise path. If you travel the clockwise path, you get to the methyl group quickly, whereas if you travel the counterclockwise path, it would take you a long time to get to the methyl group. So this does have a stereocenter. Is carbon 1 a stereocenter in this molecule?
Yes.
Yes, because you still get to the methyl group quicker if you travel clockwise rather than counterclockwise. So this does have one stereocenter. Or actually, so this is a stereocenter. By the way, how about carbon 3 here? Is carbon 3 a stereocenter?
Yes.
So there's actually stereocenters here, 1 and 3. Was carbon 2 a stereocenter here?
Yeah.
So there was really two stereocenters.
Okay.
Is carbon 1 a stereocenter in this molecule?
No.
How about carbon 4?
No.
Right. Because now the clockwise and the counterclockwise paths are identical. Now it will take you 3 carbons to get to the methyl group if you travel clockwise, but it'll also take you 3 carbons to get to the methyl group if you travel counterclockwise. So neither 1 nor 4 is a stereocenter in this case. So this is a real important skill to build up the ability to quickly see whether something's a stereocenter or not. I think you were tested on stereochemistry on prelim 2, is that right? Stereochemistry was tested on the second prelim.
Yes, it was.
Yeah. However, that's a subject that's not going to go away. That's going to be still tested in the terms of reactions on each of the next tests. That's why we need to review that now. So we need to be able to quickly identify stereocenters. It won't be tested in as much detail as last test, but you still need to be able to quickly identify stereocenters. We'll see why shortly. So we just went through that skill. Now remember, if there's a stereocenter, you need to draw wedges and dashes. Without a stereocenter, you don't need wedges and dashes. This is a little bit subtle. It's never wrong to draw wedges and dashes. It's never wrong to draw wedges and dashes because there's always something in front and something behind, but you don't need the wedges and dashes unless there's a stereocenter. So it's better not to draw the wedges and dashes if you don't need them because they just complicate things. So it's not wrong to draw the wedges and dashes without a stereocenter, but it's not useful. So does this molecule have a stereocenter?
The first one, no.
So do we need wedges and dashes here?
No.
No. Does this molecule have a stereocenter?
Yes.
So do we need wedges and dashes here?
Yeah.
Yeah. So the way I drew this was not really informative. I should have drawn maybe the bromine on a wedge, and then the hydrogen would be on a dash, or you could just leave it out as a hidden hydrogen. Do you remember, what does a wedge mean?
It means it's coming out of a page.
That's right. And what would a dash mean?
It's going back into the page.
That's right. So this molecule should be drawn with the bromine either on a wedge or a dash. If you don't use wedges or dashes, you're not really specifying the molecule here. So do I need wedges and dashes for this picture?
No.
No. You don't need it for this picture. It wouldn't be wrong to put the bromine on a wedge, but it's not really very useful. It's better to keep things simple. Do we need wedges and dashes for this picture?
Yes.
Because we have stereocenters. Now here there's many possibilities. For example, these could both be on dashes, or one could be on a dash, and one could be on a wedge, or the other one could be on a dash, and the other one could be on a wedge, or they could both be on dashes. There's many different possibilities, and you can't tell which one you're dealing with unless you draw the wedges and the dashes. Do we need wedges and dashes for this picture?
Yeah.
Yeah. All right, and this one I'm not going to ask you about because this one's actually more subtle. This doesn't have stereocenters. This actually would need wedges and dashes for a different reason, but I don't think we need to cover that yet. So I'll erase this one. That's more complicated than we need to get to yet. For the most part, if you don't have a stereocenter, you usually don't need wedges and dashes. That's as much as we need to get into right now. Okay. Does this molecule have any stereocenters?
No.
So carbon 2 is not a stereocenter?
No, because it has two CH3
Good.
groups.
So I was trying to trap you here. Most people say this is a stereocenter because they get confused by the wedge. A lot of people have a bad habit of thinking that if there's a wedge or a dash, it has to be a stereocenter. But this is not attached to 4 different groups, so there's no stereocenter. It would probably be better in this case, therefore, to draw the molecule like this. There's nothing wrong with drawing it like this, but the wedge is not necessary, so this would probably be simpler. Does this molecule have a stereocenter?
Yeah.
Which one?
3.
Yeah. So here you have to draw the wedge. If you drew the bromine on a dash, that would be a different molecule. If you drew the bromine on a dash here, that would be a different molecule. That would be what you learned before is called the enantiomer. Okay, so that's one important point to go through. So let's look at the examples we've done so far. We didn't think about that before. Do we need wedges or dashes for this picture?
No.
Because there's no stereocenter, so we did that correctly. Do we need wedges or dashes for this SN2 product?
No.
Because there's no stereocenter, so we did that one correctly. Do we need wedges or dashes for this SN2 product?
No.
Because there's no stereocenter, so we did that one correctly. And do we need wedges or dashes for this SN2 product?
No.
Because there's no stereocenter. Well, that's no accident. I was only giving you examples where we didn't need the wedges or the dashes because we hadn't learned about that yet. So far
Okay.
we've been doing all of these correctly, but now we have to get to harder problems. All right, so let's see. Now, something else that we're going to have to think about is because there are stereoisomers, like enantiomers, some reactions will give you one product and some will give you 2 products. So we need a rule for figuring out the difference between that. So here's the rule. When you attack something tetrahedral, you get one product. When you attack something trigonal planar, you get 2 products, if possible. All right, so here's an important rule that we'll be using on lots of reactions. If you attack something trigonal planar, you get 2 products. But if you attack something tetrahedral, you get 1 product. What's the geometry of this carbon? Tetrahedral or trigonal planar?
Tetrahedral.
Because it's sp3 hybridized. That's right.
Mm-hmm.
What's the geometry of this carbon?
It would also be tetrahedral.
Right. What's the geometry of this carbon?
Trigonal planar.
Because it's sp2 hybridized. Good.
Mm-hmm.
What's the geometry of this carbon?
It would be trigonal planar.
Because carbocations are sp2 hybridized.
Mm-hmm.
Okay, so if we did a reaction that attacked this carbon, we would probably get 2 products.
Mm-hmm.
Or at least we could possibly get 2 products. Maybe I should draw it like this. So we could possibly get 2 products. Or if we attacked this carbon, we could get 2 products. But if we attack this carbon or this carbon, we're only going to get 1 product. Okay, so that'll be a important rule for us. And maybe we should go over one other idea, which is the single swap rule.
Okay.
Making a single swap inverts the stereochemistry. For example, this is a molecule that has R stereochemistry. Now let's say that I do this. Do you see why I would call this a single swap? Which 2 groups did I swap? To go from here to
You
here.
swapped the carbon and the iodine.
Now I actually didn't swap the carbon. I swapped the iodine with the hidden hydrogen.
Oh, okay.
But that's still a swap. I swapped the iodine with the hidden hydrogen. That would be clearer if I had drawn the hydrogen each time. So, if I tell you that this has R stereochemistry, what's the stereochemistry here? It must be S if you believe the single swap rule. So the single swap rule makes it easy to see how to get the opposite stereochemistry. You just make a single swap. So, for example, it's usually easiest to swap the things that are on the wedges and the dashes. So here we had that single swap. You don't have to swap the things on the wedges and the dashes, but that's usually the easiest thing to do.
Mm-hmm.
So let's figure out where should you put the heads and the tails of your electron pushing arrows for this reaction.
Okay, so you have bromine with the negative charge.
Because it's bonded to the sodium. Good.
And that's the start of the first arrow, and it goes to the second carbon. And then the second arrow goes from the bond between the iodine and second carbon to the iodine.
So which bonds do we need to erase, and which bonds do we need to form, and which charges do we need to change?
You need to form a bond between the bromine and the second carbon and erase the bond between the iodine and the second carbon. And the bromine's charge goes away, and the iodine gets a negative formal charge.
Okay. Now, in this picture, do we need to use wedges and dashes?
Yes,
How do you know?
because carbon 2 is a stereocenter.
That's right. So that's a new issue we haven't had to deal with before. Now, are we going to get one product or two products here?
1,
That's right. How do you know?
because it's tetrahedral.
Who's
Carbon
it?
2.
Carbon 2. Carbon 2 was tetrahedral when it was attacked. According to our rule, we're only going to get one product then. So that means we should either put the bromine on a wedge or on a dash, but we shouldn't do both. Do you remember from class which one it is? Should the bromine be on a wedge or a dash?
I don't remember.
Okay, that's fine. So let's talk about that. Now, when so in the starting material, where was the iodine? In front or in back?
It was in the back.
Do you remember, what did we say was the big obstacle to SN2 reactions?
Steric hindrance.
That's right. That's good that you remember that. The big obstacle to steric hindrance, the big obstacle to SN2 reactions is steric hindrance. So, which side is going to have more steric hindrance to the bromine? Which side is going to be harder for the bromine to attack, in front or in back?
In the back.
Because there's a big iodine there that's blocking the back. In front, there's just a small hydrogen. That's not as much steric hindrance. So which side will it be easier for the bromine to attack from in front or behind?
From the front.
So should the bromine end up on a wedge or a dash?
On a wedge.
That's the answer. Okay. So
Okay.
now we've learned about the stereochemistry for SN2. Notice that each of these things we're going over has to be memorized, but also we're trying to give a reason for each of them. It's also important to know the reason because that makes it easier to remember it, and also because you might be asked about the reasons on the test. All right. So do SN2 reactions, does an SN2 reaction retain the original stereochemistry or invert the original stereochemistry?
It inverts the original.
It inverts. That doesn't exactly mean that you have to go from R to S, because the priorities might change when you change the groups. But spatially, it's going to invert the stereochemistry. In space, things are going to be in opposite stances after SN2. SN2 inverts the original stereochemistry. The easiest way to show that is to make a single swap. So for example, another way to do this is you might have drawn this. Suppose we draw this molecule. Would you say this molecule has the same stereochemistry or the opposite to the original molecule?
That would have the same.
So it's not the right answer for SN2. What could I do to invert the stereochemistry? Well, make a single swap. And you could swap any two groups around carbon 2. You could swap any two groups around carbon 2. For example, if you wanted to, you could have done this. This would be the right answer. This is a correct answer. This has inverted the stereochemistry because we swapped the two carbon chains. But that's probably not the easiest thing to do. The most intuitive thing to do is instead to swap the thing that's on the wedge with the thing that's on the dash. So this would also be a correct answer, and this is the easier way. This is what we wrote originally. So either of these two pictures would be correct because they both have made a single swap from the original
Okay.
stereochemistry. But usually this is going to be the picture that's easier. This is the one we started with. So this would not be the right answer, and either of these would be right. I think this one is the one that's the easiest to draw. So that's something we have to watch out for now on every SN2 reaction. Every single SN2 reaction we do for the rest of our lives, we need to ask ourselves, are we forming a stereocenter? And if we're forming a stereocenter, we need to invert the stereochemistry. Why did we not have to do that on any of the problems I gave you before? Because those problems didn't have stereocenters. So from now on, you always have to check whether there's a stereocenter or not. Now, how do we know that the bromine is only on the dash and not on the wedge? Because we know that we're only getting one product because we're attacking something tetrahedral. So do SN2 reactions give you one product or two products?
They give you one product.
One product. Because in an SN2, you're always attacking a tetrahedral carbon. In an SN2 reaction, you're always attacking a tetrahedral carbon. So you always get one product. So here we have some important rules for SN2 reaction. We're learning a bunch of the rules. Here's another rule for a SN2 reaction. All right. So let's try to draw the electron pushing arrows for this reaction.
Okay, so the negative charge is on the carbon.
Which carbon?
5.
Because it's ionically bonded to the sodium. Good.
And that goes to the second carbon, the negative charge. And then the second arrow goes from the bond between carbon 2 and bromine to the bromine.
So now we need to decide which bonds to form and which bonds to break and which charges to change.
Okay, so you form a bond between the carbon 5 and carbon 2. And then the bond between the bromine and carbon 2 breaks. And the charge on carbon 5 goes away. And bromine picks up a negative charge.
So is this the answer?
No, because you need a dash
Good.
between the carbon 2 and carbon 5.
So is this the answer?
Yes.
Okay, good. All right, so that's our new skill. From now on, we have to think about the stereochemistry as well. So that was correct. Why is it easier for the cyanide to come in from behind?
Because it's only a hydrogen back there instead of a bromine, and that has more steric hindrance.
That's right, because what's the big obstacle to SN2? Steric hindrance. Good. By the way, this is called backside attack.
Okay.
SN2 always has a backside attack because the leaving group is blocking the front side. This would also be called backside attack, even though it's coming in from in front. What we mean by backside is it's coming in opposite to the leaving group. The nucleophile in an SN2 always comes in opposite to the leaving group because the leaving group is blocking one side. Okay, so then this would give us the correct product. What's the name of this nucleophile?
Cyanide?
Yeah, that's a pretty common nucleophile, so that's a name that's worth knowing. In cyanide, is the negative formal charge on the carbon or on the nitrogen?
Oh, it's on the carbon.
That's right. That's something that you could prove by counting the the lone pairs and using chemistry skills. But that would probably be a pain. So it's better to just memorize that in cyanide, the negative charge is on the carbon, We just need to memorize that in cyanide, the negative charge is on the carbon. Okay, so that gave you the correct product here. That was a good answer. Okay, so let's draw the arrows here.
Sorry, I'm just drawing it in
Yeah,
my
take your time.
book. Okay, so you have the bromine with the negative charge, and that will go towards carbon 1. And then the electrons in the bond between carbon 1 and iodine will go to iodine.
So how should we modify this picture to show the product?
So you add a bond between bromine and carbon 1. And then break the bond between carbon 1 and iodine. And then get rid of the charge on bromine. And add a negative charge to iodine. And then bromine has a dashed line for its bond.
Because what's the name of the mechanism that you were doing in this problem?
Backside attack.
Yeah, or the name of the mechanism is SN2, and we know that inverts the stereochemistry. What about carbon 5? Should that be on a wedge or a dash?
It should stay on a wedge, I think.
That's right. Why is that common sense that that's not going to change?
Because it's not affected by the reaction.
That's right. That should seem obvious, but students often get that wrong. Remember, the only changes that we make are the changes that the electron pushing arrows tell us to make. We don't make any changes the electron pushing arrows don't tell us to make. This bond is not participating in the reaction because it's not at the head or the tail of any arrows, so it should be completely unchanged. So remember we said earlier that SN2 inverts the stereochemistry? Well, we don't mean it inverts the stereochemistry everywhere. It only inverts the stereochemistry at the alpha carbon that's getting attacked. That's something that might come up on the test. This is also a stereocenter, but it's not being attacked, so its stereochemistry doesn't change. That's good that that was clear to you. Okay, I think you're getting good at drawing the mechanisms. So now let's try to draw the product without doing the mechanism. What would the product of this reaction look like? Let's try to do that without drawing the mechanism now.
Okay. So you'd have chlorine in the place of iodine. And you would have a negative iodine ion. And yeah, that's it.
So this would be your answer?
Hold on. Oh, but do you need a wedge or something? Because no, never mind.
So would this be your answer?
Yeah.
Do we need wedges and dashes?
No.
How do you know?
Because it's not a stereocenter.
Yeah, the alpha carbon was not a stereocenter. So this was just going back to the easier questions we started with. In this case, we don't need wedges and dashes. It wouldn't be wrong to draw a wedge or a dash, but it's kind of misleading, so it's better just to leave it like this. Okay, so with practice, you need to learn how to do any of these reactions either with the electron pushing arrows or without them. So that's what we did in this case. Okay, good. Okay, there's some other details that you might be tested on for SN2, but I think the best thing now would be move on to another type of reaction. So let's take a look now at a SN1 type reaction. So let's say we've got this. So let me ask you first, could we do an SN2 reaction here? Would SN2 be possible?
No,
Why not?
because the alpha carbon is tertiary.
Yeah, we have a tertiary alpha carbon, so we can't do a SN2. Too much steric hindrance. It turns out there's another reaction we can do here, which is called a SN1 type reaction. So let's try that SN1 type reaction. Now, do you remember how many steps were there in an SN2 reaction? How many steps were there in the SN2?
1.
So it turns out that an SN1 has 2 steps. Again, the numbers here are misleading. This is actually 2 steps.
That's kind of mean.
Yeah, so hopefully we'll have time to explain where those numbers are coming from, but so far they seem kind of misleading. All right, so there's 2 steps here. Go back to SN2 for a second. Remember there's only 1 step in the SN2 reaction? What happened in that 1 step? There were kind of 2 arrows. Well, what happened in the 1 step of an SN2 reaction?
You have a nucleophile attacking an electrophile.
Good.
And then you have a leaving group taking electrons.
And leaving the alpha carbon. Good. Mm-hmm. The same exact things happen in an SN1. The same exact things happen in an SN1, they're just split into 2 steps. So now step 1 is the leaving group leaves. Step 1 is the leaving group leaves the alpha carbon, and that's what would happen then in step 2.
The nucleophile would attack the electrophile.
Yeah, the alpha carbon. Then the nucleophile joins the alpha carbon. So do you see, that's exactly the same thing that happened in SN2. It's just we're pacing it out into 2 separate steps now. Okay. So it's crucial to memorize that these are the steps. So can you figure out then what would be good arrows for step 1 here? If I tell you this is going to be an SN1 reaction, what arrow do you need to show the leaving group leaving the alpha carbon?
You would need an arrow starting from the bond between carbon 2 and iodine and going to iodine.
Good. So what role is the iodide going to be playing?
Leaving group.
And how do you know it's a good leaving group? How do you know this is an acceptable leaving group?
Because it's one of the ones we memorized.
That's a good answer. Yes. That might seem obvious, but for example, you're not going to do this. You're not going to do this because hydrogen is not something we've learned as a leaving group. It's only the iodine that we've learned as a leaving group. Also, you're not going to do this because carbon is not something we've learned as a leaving group. All right. So that's all that happens. Now there's only 1 arrow in that first step. Now remember, we're supposed to use the redraw and modify technique. So let's try to do that carefully. So now we need to go through our process again for using electron pushing arrows to draw the product of a step. So we did step 1, we redrew the starting materials. Now we have to look at the arrow and decide if it's breaking a bond or forming a bond or both. So is this breaking a bond or forming a bond or both?
It's breaking a bond.
So which bond should we erase?
The bond between carbon 2 and iodine.
That's right. We need to be precise, like we were doing a math problem. And that was the only arrow. So that's the only thing we have to do for step 2. Now we have to do step 3. So first of all, we look at the atom that's losing electrons from the initial tail. So who is the atom that is losing electrons from the tail here?
The alpha carbon.
Yeah, carbon 2. It's losing the electrons in this bond. So what should be its new charge?
Positive.
That's right, because it started neutral. It started with a neutral formal charge. By the way, remember, we're not using delta charges here. This is about formal charges. I should have put that in the handout. So this here is going to be, this started neutral and it ended up positive because it lost electrons. I think this is the first example we've ever done where we made a positive charge. But notice we can figure that out just from the logic of the situation. If you start with 0 formal charge and you lose electrons, you should become positive. And then who's the atom that's gaining electrons from the final head?
Sorry. Iodine.
So what should its new charge be?
The iodine would get a negative charge.
Good. By the way, I should have mentioned we can check our work. What was the overall net formal charge of this entire molecule?
0.
And what's the overall net formal charge of these reagents?
Also 0.
That tells us we did it right. You can always check that you got the charges right because the net charge before the reaction has to be the same as the net charge after the reaction because of conservation of charge. So that's a good way to check things. So the thing that I'm trying to convince you of is, even though you've never seen this reaction before, or even if you had never seen this reaction before, if someone drew this arrow for you, you should be able to figure out these products on your own. You don't need to have the reaction memorized. The arrows tell you exactly how to draw the products of a step. Most students don't seem to realize that. They seem to think that they have to just memorize each reaction, but the arrows tell us what we're going to be drawing. Okay, so that was our step 1. That was step 1 of our SN1 reaction. So what do you think is going to happen in step 2?
So then you'll have the bromine with a negative charge as the nucleophile, and that will go towards the carbon 2 with a positive charge.
Good. So what role is carbon 2 playing?
Electrophile.
Good. And I think you already mentioned, how do we know that carbon 2 is a reasonable electrophile?
Because it has a positive charge.
It has a full formal positive charge. That's right. In fact, this is a better electrophile than any of the ones we've used before. Remember, in all the previous problems, we didn't have a positive formal charge. We had to settle for a delta positive. But now we have an even better nucleophile because the leaving group has already left. Here we have a full formal positive charge. And also, this is a great electrophile because it has an incomplete octet. That also makes it want to receive more electrons. So that's our step 2, the nucleophile joining the alpha carbon. So now again, we have to go through this method. Step 1, redraw the starting materials. Then step 2, we need to decide which bonds we're breaking and which bonds we're forming. So which bond should I erase or break here?
You should form a bond between the bromine and the second carbon. And then you can erase the formal charges on carbon 2 and on the bromine because they cancel.
That's right. How do we know that carbon 2 is going to end up with a neutral formal charge?
Because the overall molecule has to have a neutral charge.
That's a good answer. How else do we know that carbon 2 is going to end up with a neutral formal charge?
Because it's gaining electrons.
And because what charge did it start with?
A positive one.
Right, that's important, right? If carbon 2 had started neutral, it would end up negative. But because it started positive, it's ending up neutral. Okay, good. So here's our product. And did you think about the stereochemistry? Do we need wedges or dashes here?
You don't, because it's not a stereocenter.
That's right. That's something we always have to check. So here's our final product. We've drawn the final product. So that's our first example of doing an SN1 reaction. Now we've done our first example of an SN1, and we've also seen how the arrows tell us exactly what products to draw once we've drawn those arrows. So this was the same as for an SN2, just split up into 2 steps. Now the leaving group leaves first, and then the nucleophile joins. So these steps have to be memorized. You need to know from memory what happens in step 1 and what happens in step 2 of a SN1 type reaction. Okay, that was good. Okay, so let's try to draw the arrows. Where would the heads and the tails of the arrows go now?
Okay, so you have one going from, hold on. So first you have the leaving group go. So you have from the bond between carbon 3 and chlorine going to the chlorine.
Do we need any other arrows for that step?
No.
Good. So what's the name of the mechanism that you're doing here?
SN1.
How do you know you're not doing it? How do you know that you shouldn't do an SN2?
Because the alpha carbon is tertiary.
That's right. So there's be too much steric hindrance for that. Good. So how should I modify this picture to show the product of that step?
You erase the bond between chlorine and carbon 3 and give chlorine a negative charge. And give the alpha carbon a positive charge.
That's right. So on every step of every mechanism, how many charges are we going to change?
2.
Yes, we always or almost always change 2 charges because there's always going to be an atom at the initial tail and there's always going to be an atom at the final head. So that's something that's very important to get in the habit of doing. On every step of every mechanism, we always change 2 charges, and that is the most important part of drawing the products correctly. The bonds are important, but the charges are even more important because it's the charges that tell you what's going to happen next. All right, so now where would you put the heads and the tails of your electron pushing arrows for the next step?
So then you take the negative charge from the iodine, and that goes to carbon 3.
Good. So how should I modify this picture to show the product?
You form a bond between iodine and carbon 3, and you get rid of the formal charges on both of them.
So what role was carbon 3 playing in that step?
The electrophile.
Good. And why was that reasonable?
Because it's gaining electrons.
But how do we know it wants to gain electrons? How do we know it's reasonable?
Oh, because of the positive charge.
Right. This is what I was saying before. That's why it was so crucial to get this charge right in this picture. If a student forgets to draw this charge, then there's no way to figure out what's going to happen in the next step. That's why I said that the charges are actually even more important than getting the bonds right. Most students kind of think of the charges as an afterthought, but the charges are the main point of each picture. How do we know we're done now? So, of course, we kind of memorized that there's only 2 steps, but the general rule is, do you remember, does nature like things to be charged or neutral?
Neutral.
So the general rule for organic chemistry is, as long as your main molecule has a formal charge, you're probably not done, and you need another step. And when the main molecule has 0 formal charge, you might be done, and you don't need any more steps. For example, that would be a clue that this is not the final product. This doesn't look like a final product because the main molecule still has a formal charge. Whereas this looks like it probably might be the final product because now the main molecule has no formal charge. So that would be a good way to attack this. Did you think about stereochemistry? Do we need wedges or dashes here?
No,
That's right. Why not?
because it's attached to 2 of the same groups.
Good. So it's not a stereocenter.
Mm-hmm.
Okay. So what we need to do now is, remember that what we did for SN2 is we figured out what was good or bad for SN2. We figured out the big obstacle to an SN2, and then we figured out how we could speed up or slow down an SN2 reaction. So we need to do that for SN1. So first of all, remember, how many steps are there in an SN1 reaction?
There's 2 steps.
2 steps. What happens in the first step?
The leaving group leaves.
And what happens in the second step?
The nucleophile goes to the electrophile, adds.
That's right. Which of those do you think is the hard step? Which one does nature not like? Step 1 or step 2?
Probably step 2.
Any particular reason?
No.
Okay.
It's
Well,
just
remember,
the feeling.
what is it that nature doesn't like? Nature doesn't like charges. Nature doesn't like charges.
Okay, yeah, so probably step 1, because that's creating charges.
Yeah. In particular, the key charge that it's creating that nature doesn't like is this positive charge on the carbon. Nature doesn't like carbocations. In fact, this is doubly bad because not only does this have a positive charge, but it also has an incomplete octet. Nature doesn't like that either. So which step is the hard step? Step 1 or step 2?
Step 1.
Nature likes step 2 because then you're getting rid of some charges. So nature likes step 2. It doesn't like step 1. So which is the slow step? Step 1 or step 2?
Step 1.
So which is the rate determining step?
Step 1.
And that turns out to be the key. So what that means is only things that participate in step 1 affect the rate of an SN1 reaction. Anything that only participates in step 2 does not affect the rate of an SN1 reaction. So for example, does the leaving group ability affect the rate of an SN1? Well, does the leaving group participate in the rate determining step?
Yeah.
Because it leaves in that first step. So does leaving group ability affect SN1 reactions?
Mm-hmm.
So we still need a good leaving group, just like for SN2. Does the nucleophile participate in the rate determining step?
No.
It doesn't. It waits until step 2. So do we need a good nucleophile for an SN1 reaction?
No.
That's a very important idea. SN1 can use a poor nucleophile. Why does the nucleophile not matter? Because it's not in the rate determining step. What do I mean by poor nucleophile? What would be an example of a poor nucleophile?
A neutral oxygen.
Right, oxygen with no formal charge. That's the only thing we've learned as a poor nucleophile. Of course, SN1 could still use a good nucleophile too. So all of the nucleophiles that we've learned that work for SN2, they also work for SN1, plus oxygen with no formal charge. So SN1 can use either a good or a poor nucleophile. But SN2 can only use a good nucleophile. All right, so that's one important idea. Remember, what was the big obstacle to SN2?
Steric hindrance.
Steric hindrance that blocks the nucleophile. But that doesn't matter for SN1. Can you think, why does steric hindrance that blocks the nucleophile, why does that not make any difference for SN1?
Because the nucleophile isn't involved in the rate determining step.
That's right. It doesn't matter if there's any steric hindrance for this step, because this step is fast anyway. This step is so fast anyway, steric hindrance wouldn't make any difference. So steric hindrance is not an issue for SN1. What is the issue for SN1? Well, remember that the big problem with SN1 is the carbocation. So the big obstacle to SN1 is stabilizing the carbocation. What I mean by that is that anything that stabilizes the carbocation is good for SN1, and anything that destabilizes the carbocation is bad for SN1. Now, to think about this, we need to learn, compared to hydrogens, are carbon chains electron donors or electron withdrawers? So we can go over that. Compared to a hydrogen, is a carbon chain an electron donor or an electron withdrawer? Well, the answer is carbon chains are electron donors. They're not strong electron donors, but they're weak electron donors. And there's a pretty simple reason for that. A carbon chain just has way more electrons than a hydrogen. A hydrogen just has two measly little electrons in the bond. A carbon chain has a whole cloud of electrons. So it makes sense that a carbon chain can donate more electrons than a hydrogen can. So we need to memorize this. Carbon chains are electron donors. This will be important for a lot of reactions in this class. Let's say that you have something with a negative formal charge. Will that be happy or unhappy?
It would be unhappy.
How could we make it happier? Would we make it happier by attaching it to electron donors or by attaching it to electron withdrawers?
To electron withdrawers.
Because would that intensify the negative charge or spread out the negative charge?
It would spread it.
Yeah. Do you think nature likes charges to be concentrated or spread out?
Spread out.
Because that kind of reduces the charge in any one place. So an electron withdrawer would pull the negative charge away from this place and spread out the negative charge. So negative charges are happier attached to electron withdrawers. Let's say you have something that has a positive formal charge. Is that happy or unhappy?
Unhappy.
Because nature doesn't like charges. How could we make it happier?
You attach it to an electron donor.
Right. Because the electron donor will donate electrons to the positive charge and make it less positive. Rather than saying it'll be happier, maybe we should just say it's less unhappy. But that's the basic idea. All right. So which of these two molecules is happier? Which of these two species is happier, A or B?
I have no idea.
Now, does the positive charge make you happy or unhappy?
Unhappy.
So what's the difference between these? The difference is this has a carbon chain, and this doesn't.
Okay.
Is the carbon chain going to make the positive charge happier or less happy?
Oh, the carbon chain is a donor, an electron donor, so it'll make it happier.
So which of these two molecules is happier?
B.
Yeah, B is happier than A. B is happier than A. So we're putting together the different pieces we were going over. Carbon chains are electron donors, and positive charges are happier when they're attached to electron donors. So positive charges are happier when they're attached to carbon chains. You can see what's going on here. These hydrogens have almost no electrons to donate to the positive charge, whereas here we've added a whole cloud of electrons that can help to stabilize that positive charge. Who's happier, C or B?
B. C, sorry.
Which one?
C, because it would be more spread out,
Who's it?
the charge,
Yeah. How do you know?
because there's more carbon chains, which are more electron donors.
That's right. So you I didn't tell you this, but it sounds like you figured it out. If you have a positive charge, do you want to have more or fewer carbon chains? Does a positive charge want to be attached to more or fewer carbon chains?
To more.
Because each carbon chain is an electron donor. So the more carbon chains, the better in this case. So now
Yeah.
C would be happier. C would be happier than B. So who's happier, D or C?
D,
And why's that?
because it's attached to more carbon chains.
That's right. So how could we classify these? What type of carbocation is this? Primary, secondary, or tertiary?
Tertiary,
And this?
secondary,
And this?
primary,
And do you know what we would call this?
methyl,
Yeah, this is a methyl because it has no carbon chains. So which type of carbocations are happiest?
tertiary,
And which are the least happy?
methyl.
Methyl and then primary. Okay, good. So this will turn out to be very important again for the whole course. Tertiary carbocations are the happiest, then secondary, then primary, then methyl. Good. Now, it doesn't really matter how long the carbon chains are. For example, suppose I started writing this one like this. Making the carbon chain longer does not have a big impact. It has a small impact, but not a big impact. So it doesn't really matter how big the carbon chains are. The most important factor is just how many carbon chains there are. Tertiary would be best. Now, also, we should take a look at this. So, which of these two molecules is happier?
B,
And why is that?
because it's connected to more carbon chains.
Who's it?
The charge.
Yeah, the carbocation. Why are the carbon chains good for the positive charge?
Because they're electron donors.
That's right. Now I'm going to ask you a trick question. Which of these two molecules is happier, C or D?
Wouldn't they be the same?
That's right. But wait a second, this one has a tertiary carbon. Why doesn't that make it happier?
Because they're all neutral, so.
Yeah. Okay, good. So it's good that you didn't fall into that trap. A lot of students misunderstand this. A lot of students just say, oh, tertiary is better than secondary. But that's not true. What we're trying to say is tertiary carbocations are better than secondary carbocations. When things are neutral, they don't care very much how many carbon chains they have because neutral things are already pretty happy. So these are about equally happy. So my point is, I think you're already understanding this. Don't just say to yourself, tertiary is better than secondary. You have to say, tertiary carbocations are better than secondary carbocations. When things are neutral, they don't care much whether they're primary, secondary, or tertiary. Okay, good. So do you remember what was the big obstacle to an SN1 reaction?
Stabilizing the carbocation.
So what type, and remember who's going to form the carbocation? The alpha carbon.
Mm-hmm.
So which type of alpha carbon would be best for SN1? Primary.
A tertiary.
Yeah, this would be best for SN1. Because a tertiary alpha carbon will form the most stabilized carbocation. So then secondary would be not as good. What type of alpha carbon would be worst for SN1?
Methyl.
Right. So this would be worst for SN1. In fact, it turns out that primaries and methyls are so bad they can't do SN1 at all. You can't do an SN1 at all. You can't actually form a primary or a methyl carbocation. You usually can't even form a primary or a methyl carbocation because nature hates that so much. Nature won't even form them in the first place. You can only form generally secondary and tertiary carbocations. So that gives us that pattern. So So which of these is best for SN1?
For SN1, it would be tertiary.
And which ones can't do SN1 at all?
Methyl and primary.
Which of these would be the best for SN2?
Methyl.
And who can't do an SN2 at all?
Tertiary.
Why can't it? Why is tertiary so bad for SN2?
Because of the steric hindrance.
That's right, because what's the big obstacle to SN2?
Steric hindrance.
That's right. Why is tertiary so great for SN1?
Because it stabilizes the carbocation the best.
That's right, because what's the big obstacle to SN1?
Stabilizing the carbocation.
Okay, so all these things are now coming together. So notice, if you have a primary alpha carbon, what type of reaction do you think you'll probably get?
SN2.
Yeah, you can't do an SN1. And if you have a tertiary alpha carbon, what type of reaction are you probably going to get?
SN1.
You certainly can't do SN2. What if you have a secondary alpha carbon? Well, then so far we can't really tell, right? This is the pesky one. Secondary alpha carbons could conceivably go either way. We haven't quite learned enough yet to figure out which one that would be. But if you have a primary, you know it's probably going to be SN2. Definitely can't be SN1. And if you have a tertiary, it's probably SN1. It certainly can't be SN2. The secondary one is the one that would still be a little bit undecided. So looking at the examples that we did so far, is this a good candidate for an SN1?
No. Oh, sorry, for SN1, yes.
Because
it's tertiary.
Tertiary alpha carbon. Could it have done an SN2?
No.
So it was reasonable for us to do an SN1 in this example. And the first example we did was this one. Would this be a good candidate for SN1?
I'm sorry, which one are you pointing at?
Would this
Oh,
molecule be
okay.
a good candidate for
Um,
SN1?
that would be for SN2? No.
Not for SN2. Would it be a good candidate for SN1?
Yes.
And that's what we did in this case. We did it as a SN1. How about the first example we did? Here's the first example we did today. Would this be a good candidate for SN1?
No.
How about for SN2?
Yes.
Yeah, and that helps to explain. So when we first did this problem, I just told you that it was an SN2 reaction. But now you have the tools that would allow you to predict that this probably will be an SN2 and probably won't be an SN1. So what type of reaction would we predict here?
SN2.
Because
It's not, sorry, because it's the alpha carbon is primary.
right. Notice it doesn't matter what the other carbons are. This carbon is secondary, but what matters is the alpha carbon, which is primary. So when we did this reaction again, I think I just told you that this was an SN2. But now you've built up enough tools that you could have predicted that this would probably be SN2. It certainly wouldn't be a SN1 type reaction. Okay, so to summarize what we've gone over here, so far we've learned what happens in an SN1 or an SN2 reaction. SN2 is one step and SN1 is 2 steps. And we've learned the real key to memorizing all this is remembering these big obstacles. So I really encourage you to memorize these. The big obstacle to SN2 is steric hindrance. The big obstacle to SN1 is stabilizing the carbocation. We didn't get to E1 and E2 yet, but we've explained a lot of the details here for SN1 and for SN2 in this table. And how many steps are there in a SN1 reaction? How many steps in an SN1 reaction?
2 steps.
Good. Which is the rate determining step?
The first step.
And what happens in the first step?
The leaving group leaves.
The alpha carbon. How many molecules participate in the rate determining step for SN1? How many molecules are participating in the rate determining step for SN1?
One molecule.
Just this one here.
Mm-hmm.
So notice the nucleophile is not participating yet.
Yeah.
That's where the number 1 comes from.
Oh, okay.
That's why this is called SN1. Remember how we were complaining that this was not a very helpful number because there's actually 2 steps here. The reason they call this 1 is because it's so important to know what's participating in the rate determining step. This is called unimolecular because there's only 1 molecule in the rate determining step.
Okay.
Now, what's the rate determining step for an SN2 reaction?
The only step.
The only step. How many molecules participate in that rate determining step?
2.
2. Both the electrophile and the nucleophile participate. So that's where the number 2 comes from. They call this a bimolecular reaction because there's 2 things participating in the rate determining step. So that's probably not the most useful nomenclature because it's even more important to know that this is 1 step. So the number here does not tell you the number of steps. It tells you how many things participate in the rate determining step. So we kind of explained that thing that was a little mysterious before. All right, I should have mentioned, hopefully you've been copying down all the examples that we've done today. Most of these examples took us, 5 or 10 minutes to talk through the logic of each one. But you need to practice these over and over so that you can do each one in about 30 seconds or so. You need to keep practicing these until these are easy because each part of organic chemistry keeps building on the previous part. So you need to practice these until these are easy. So it would be good to just go back and do all these examples over again, but enough times that you can make sure that those are easy for you. That's the only way that you can start building even more reactions on top of that. So we went over a lot of stuff today that has to be memorized, but we also tried to explain as many things as we could, and you have to work on both of those. You need to memorize a bunch of stuff, but as much as possible, you need to understand why the rules that you're learning work too.